financed by Embrapi and MCTI on quantum technologies. The focus of these centers has a main objective of integrating research, cutting-edge research, and bring that to industrial applications. Connect the industry with the academia. And our center in particular has a special focus on quantum communications in the research area. In the education area, we also work with quantum computing. And the idea, how we do that, is partnering with research institutions. So we have many partners, as I'm going to show you later. Cimatec is a university and R&D center, which is located in Salvador. It was created in 2002 and is part of the Senai system, and as such, it has the mission of supporting the industry. Right, so the R&D we do is focused on solutions for our industrial partners. It's a relatively large organization. It has over 1,700 people, 44 areas of expertise that we use to do joint integrated research, and 6 campi. Senai is different than a regular research institution in the sense that we are driven by the market. So everything starts with a demand, and that demand can be coming from the government, from the society, or from the industry. Once we have that demand, we will assess what needs to be done. We will partner with different research institutions and choose the best funding agencies for that kind of need. And then we do the development of what that project might be. It can be both education projects as well as R&D projects. It can also be a service, a technological service, or be associated with creation of a new business. The infrastructure is increasingly, it's becoming large. You can see here in the left corner the main campus, and here is an industrial park where we do pilot planning, pilot production. We can also do large infrastructure that are more industrial in size and needs more space. Of that infrastructure, what is relevant for quantum communication is the optics and the photonics lab, the embedded systems lab, the high-performance computing center, and where we have a quantum simulator. Is a supercomputer that has an architecture optimized for simulating quantum systems. And all that infrastructure is applied to a range of different projects from the industry. When we talk about quantum technologies, probably everybody here knows about the different technologies that come from quantum information theory, and the ones that we do most work is in the quantum communication and quantum computing. So quantum computing has been on the news very frequently, non-stop, basically, since the end of the last year. And the attraction of quantum computing is that you can run simulations, the optimization routines that would be very complex to do it with a classical computer. But it has a problem. On one side, it can be used for analyzing the traffic in a network or in a location, and you can use that to identify invasions on your network, but it can also be used to break cryptographic systems or keys. So in a cryptographic system, you have a message that you want to transmit from Alice to Bob. You use a key to encrypt that data, so if it's intercepted, you can't decrypt it as long as you don't have the key. And there is different types of keys that you, or systems. You can have symmetric systems where the key is the same, and you have asymmetric where they are different. So there are two algorithms that run very efficiently in quantum computers that weaken or can potentially break those keys. And if you break those keys, the security is gone, right? So the Grover's algorithm is basically a search algorithm for unsorted data, and it weakens the symmetric type algorithm or cryptographic keys. And that's what, including the most secure protocols, cryptographic protocols that usually is the AES. It doesn't fully break, but it weakens, which means it will take less time for you to run into the right solution that if you used the quantum classical computer. Shor's algorithm is the one that there is all the rage about, because it is based on, these are cryptographic systems which are based on prime numbers. And with that, you can solve, using Shor's algorithm, this problem of factoring large numbers much faster than you would do with a classical computer. So that's a real problem. Imagine, don't imagine, but this is a node graph, but it shows the key length that was broken and when it was broken in time using classical computers. And you can see as the computational power increases, you start breaking larger and larger keys. Until recently, people would use 2048, the length of the keys would be 2048 bits or symbols, because it would allow you to, would give you security. The question is, when quantum computing is available, you're gonna gain an exponential gain in the time or the processing power, and you're gonna be able to break those keys. So today, they already recommend that you use 3072 bits, but the problem is that as you increase the number of bits, it also increases the time for encrypting and decrypting. And that is a problem. And the other point that's interesting is that if you look at last year, around this time, the Chinese already published a breaking or variant of the algorithm and breaking keys that were 50 bits with a D-Wave computer. So 50, you say, oh, it's still very far away from the 2048 that is used today, but it's a question of time, right? We don't even have very large quantum computers that are working, and they are very noisy. Imagine when you have that. So this has moved to a strong effort and an acceleration in the quantum cryptography adoption to deal with this problem. Because it's expected that in about 5 years, you're going to be able to start breaking those keys, and nothing is going to be safe anymore. So there are two approaches. One is use post-quantum cryptography, and that's a fancy way to describe a classical cryptography system that is so complex that even a quantum computer won't break, at least not for now. But there is the chance that you have more efficient key cracking algorithms, and the quantum computing power will also evolve. So we don't know if that's a long-term solution, but it's certainly a very good patch for nowadays. So there is a push for everybody to adopt post-quantum cryptography, and it's already standardized by NIST. And they standardized it with 3 algorithms, and now they already are adopting a new one as a backup, because they are not so sure, right, that the 3 will be enough. So if one is broken, you have another one. The quantum cryptography, on the other hand, has its security based on the laws of physics and not on the mathematical complexity. So it has some advantages. It also allows you for detection of eavesdropping, but it has already commercial solutions, and you have field trials all over the world, both in metropolitan networks as well as backbones. So what is a quantum key distribution system? You have Alice and Bob, and they want to have a secret key that only the two of them know, so that they can encrypt their information. So Alice prepares a quantum state, Bob detects that quantum state, and then they will use a classical process using a classical channel or a public channel to reconcile that information. And in the end, they will have a symmetric key, which will be the same for both cases. And then you can use that to encrypt and decrypt the information. There is different types of protocols that you can use for doing this quantum cryptography. You have discrete variables and continuous variables. In the discrete variables, you're encoding information in single photons, and that could be bipolarization of single photons. It's the most common way. But it's not always easy to get a single photon source, so often they use weakened coherent states. In the continuous variables, you're using coherent states, and you are coding the information in the quadrature field. The advantage here is that you don't need single photon detectors. You can deal with homodyne and the heterodyne detection, and your systems don't need any refrigeration, right? You can, and it's very similar to a classical coherent communication systems. So with that, it's completely compatible with today's systems, and it can easily be integrated, so you have scalability both of size and as well as cost. And those are important aspects. It will also more resilient to co-propagation of classical channels. It has, the other advantages has higher rates. The throughput is higher, but at the cost of a very significant effort in digital signal processing and the reconciliation effort. So how does that look? Here you look at the phase and amplitude space. You have different ways of modulating. Each of these dots or these blurs, it would be a quantum state. The traditional, the first one that was developed, it's a Gaussian state, so you have a distribution that's continuous and Gaussian. But you can also do discrete modulation and use some of the traditional telecom formats, be it phase shift keying or quadrature amplitude modulation. And quadrature amplitude modulation combined with probabilistic shaping, which is a technique used in classical communications, can give results very close to what you'd have with a quantum, with a Gaussian states. And the detection can be heterodyne, homodyne, or you can also use double homodyne. So how do you implement that? You have a signal laser, you have IQ modulation, and then you can feed that with Gaussian random variables, but you can do BPSK, which is binary phase shift keying, or quadrature phase shift keying, or QuIIN, that's quadrature amplitude modulations. And here we show how we have encoded, how that data would look like if you look for each time being that's given by the red curve. You send it to the transmission channel or the quantum channel, and then at your end, at Bob's end or the receiver end, you're gonna use a local oscillator, mix with that channel, and then do, with a balance detector, do the homodyne detection. After that, you have to do ADC, and then you go to the post-processing. In general terms, that's how we implement it, but you have many steps that are very hard. One of them is the post-processing. The post-processing starts with the DSP, and the DSP has the digital signal processing, and I'm gonna show another slide that shows how complex that is. And then you have data that's generated and detected data. After that, you have to do estimation, parameter estimation, which is basically a calibration feature, so you can calculate the expected error rate, and then analyze if the system is being, do the security analysis for knowing if you're being eavesdropped or not, or what kind of data to drop. Once you do that, you go to the reconciliation, and one of the important points of the reconciliation is that you do error correction. And there is different types of algorithms that you can use that, but that's an important point. The difficulty here is that the matrix you have to do are very large. Sometimes you're talking about, in some case, 10 to the 10th or 10 to the 20th blocks of columns or blocks that you have in your matrix. So that is complex and time intensive. And then you share some data so that you can do this correlation and find out if the errors were correct or not, and do that. And once you get after the information reconciliation, you have two correlated and corrected bit sequences, one that Alice and Bob are going to be. However, they are still not the final. They use one more step, that's the privacy amplification, and that until you get the secret rate. And the privacy amplification is a form of you shortening and compressing your data so that you have increased the security. So it's just a booster on the security. But it's, again, time intensive, classical process by time intensive. The DSP, here is the DSP for coding. So the whole thing is that you start with your quantum random number generator. You're going to do a constellation mapping, shape it, and then use that information to drive your modulator. On the other hand, on the detection side, you have your balanced detectors. You do the transimpedance amplification and then the ADC. And then you have a series of operations to clean up. Right, so you want to do the clock recovery, you want to compensate for any distortions, and for that use some static and adaptive equalization, and then you can finally recover the carry and the phase, and then you have to do the demapping and decoding. And then you have a binary output, and that's what you send for the reconciliation step. At QuiIN, we have a large program associated with those steps. We have a group of researchers working at the theory as a theoretical aspect, and we have projects around the comparison of the different protocols, the security analysis, and quantum random number generation certification. We have, on the experimental side, the building of a test bed, so you can realize, or you can do experiments both with fiber channels and free space. For the fiber channel, we're going to be looking at optimization of architecture, configuration, components, and protocols. While at the free space, we have to deal with turbulence and pointing. And that's a preamble for us to be able to go longer distances, eventually to communicate with drones, and later on with satellites. In the post-processing, it's actually almost half of our researchers are working in this area. And we are working both in algorithms as well as accelerating hardware. And the algorithms are for optimizing the DSP, digital signal processing, the parameter estimation, the error correction codes. And while the hardware, the accelerating hardware, is so that we can generate real-time keys. Only for you to have an idea, if you don't do the accelerating hardware, it might take 2 days for you to be able to generate your keys using traditional computing. So you want to have a dedicated chip, and in the absence of that, because it's too expensive, you want to encode that in an FPGA, which is a field gate, programmable gate array. We are starting an effort now on the quantum networks, and the idea here is that we can do some simulations and optimizations so we can understand the trade-offs between different topologies, where to place the trusted node, how to get around security failures with the trusted nodes. We also have an integration with the data, with the network, the classical network, and that is how we deal and how we integrate the quantum key distribution system into the overall cryptographic system. And to that, we have to deal with the key management layer and as well as the application layer. And later on, when we have our system developed and ready, we will look at coexistence with classical channels. But even if we don't do that and they are using dark fibers, we still have to do that so that we can bring that quantum key, or that key that's being generated to a useful system. It has to integrate in the classical systems. And we also looking into some aspects of cybersecurity, looking at hybrid protocols like mixing quantum key distribution with post-quantum cryptography, and doing understanding the application so we can do demonstration, be it at the MACsec, that's a security at the transport layer, or at the hardware layer, but OIPsec, that's for point-to-point cryptography, VPNs, and other applications. So our roadmap is that we are, 2024, we are doing the project planning and infra acquisition. We are installing that. We hope that by the end of the year, we'll have our first system working, but still with offline processing while you develop the hardware for accelerating, so we can integrate that in 2026 and have real-time keys. And if you're successful here, then we'll look into a measurement device independent protocols. On the free space, we are looking at, we are building a test bed for looking at the, being able to look at aspects of the turbulence and developing the pointing and system, and as well as an adaptative system for compensating for those. And the goal is that we might look at viability studies for drones and autonomous vehicles in 2006, and maybe start looking at for satellite, but more at the requirement level. And in the network, we are just going to implement a 2-node in 2025 and try to increase that to 3 nodes in 2026. So this is a large program. I've been telling you a little bit about the R&D aspect, where we are focusing on continuous variable QKD, but we also have a very significant effort in education and training. We have for both quantum communication and quantum computing. We have a program for startup creation and attraction, and a technological association. And I'll tell you a little bit more about those. Our training and education is varied from talks to workshops to mini courses, but also we have a specialization course development and some master and PhD studies integrated in existing programs. And the idea is that we can have a varied type of audience or training targets. And what we really want is to be able to raise the awareness of the need for quantum cryptography, stimulate demand, help adoption with the technology, and hopefully attract investments and lead to industrial development. There is a lot of demand for this type of education. Our specialization in quantum communication and quantum computing, we are opening 50 slots for distance learning courses. And what we received was over 250 applications for the quantum communication and 800 applications for the quantum computing. So now instead of having one only course, we're going to launch 4 for quantum computing and 2 for quantum communications. And we're having the first inaugural class next week. In the startup attraction and creation, we have many different programs, and they are associated with fostering the entrepreneurship in quantum technologies. We have expert talks, which are awareness talks that are given every month. We have different calls, one call for ideation in quantum technologies, and with support of our accelerating units and education on how you do the business plan and all that. We have a call for boot camp, a boot camp call, which helps existing startups better structures themselves, giving a lot of attention for the commercial and business side. And we have the QCI call, where we pose challenges, and then we see and then we have the startups propose solutions for those calls. And of course, that is not done in the vacuum. We are supporting that every step of the way, including adjusting the business plan, and the topic too, the technical plan. So, getting to the end of my talk, I hope I give you an idea of the amplitude of our program. And we are basically 1.5-year-old, but we already have an incredible team. We have 20 support and research staff, but we have over 50 fellows and mentors, and we are very thankful to all of them. Of course, we are thankful to the financial support from Embrapi and MCTI, as well as Senai Cimatec, and the many fruitful partnerships that we have in place, both with research institutes as well as companies. Thank you.
Questions?
This is certainly something that you said and I lost. About the, how can I say, the course in quantum communication, what is the target, undergraduate students or...
It's an specialization. É uma especialização. It's graduate studies that's lato sensu, right? So you need to have a diploma from a 4-year degree.
Okay.
And that's usually the target. The main target is engineering graduates, as well as information technology. We also have some physicists that are applying. Physics has already an idea what is needed, but they don't know the engineering side. Engineers usually don't know anything about quantum, so we try to cover all those aspects, both aspects in the course. Okay. But you don't expect that you're going to have a PhD graduating from that, right?
Sure.
It's let's say, it's not for, the objective is not that we have, is that we have the baseline. For then, some of them will go into master's and PhD programs, but it's for able to bring that engineering community to work on this.
So most of the enrolled students are not already master or PhD students elsewhere?
Well, the first, we did a trial program that was presential, right? It was in loco, and was a small group that, so we tried, and that was mixed. We had like 25% of them were already grad students. The others were not, right? Now, with this higher number of offers and being able to do it distance learning, then we expect to have a more varied background.
More questions?
I'd like to ask, you talked about the test beds for the networks, both fiber and free space. Do you have any idea of the size of those test beds?
Yeah, initially we're going to be doing it in the laboratory. So we're going to, for the fibers, just going to use spools of fibers instead of using on the ground. But we have a partnership with the Rede Rio Quântica of the Quantum Real Network. And then we're going to test those in their network, the systems that we develop. For the free space, we are also initially studying those effects in the lab, and then we're going to have an outside area in Cimatec where we can do some tests as well, and then eventually take it, whatever we develop, to also to quantum real network.
Hi, Valeria. Thanks
Hi.
for the very nice talk. I'd like to ask you to comment a bit on the, I mean, you're developing FPGAs because you need to process huge amounts of data very quickly. I mean, you're not developing the FPGAs, but FPGA-based hardware. And I wanted to know from you if you've looked into GPUs to do that kind of processing, and if you expect the FPGA hardware to outperform GPUs in the long run.
I think we looked it, but we didn't think it was going to be sufficient. Ideally, you really would like to have a custom chip designed, but you don't have volume for that. So I'm not specialist in this area, but our specialist in this area tells us that we need to go FPGA. So I'm trusting him that he's right. Of course, as GPUs are increasing, and maybe it's possible to do that, but I'm not sure if it's going to be, you're still going to have limitations, I think.
Okay, thanks.
Even though they are better optimized for solving matrix, but I think we're still going to need the LPGAs.
Hello, thank you for presentation. In the case of the CVQHD, the hardware that you are planning to use, how it's like from the scratch, you are building it, or you are building plug and play hardware that you can buy?
We are building it from components, off-the-shelf components, right? So we bought the lasers, we bought the modulators, the demodulators, or the 90-degree hybrids, and all the detection systems. Having said that, we started looking, we are talking and with the people that came from BR Photonics, the people from, today they are called Hewitt, and they have a lot of experience in integrating those. So they are helping us with that integration to speed up a little bit the process, and also understanding how you're going to be able to integrate that in the future with integrated photonics. But that is not something we are looking at yet. First, we want to optimize at the component level for then decide how to do the integrated photonics.
One last question. I'll give the priority to the student, sorry. Yeah. No? So, no. Sorry about that.
Hi, Valeria. Thanks so much for your presentation. So the bit rate that you showed there for the comparing like the single photon detection and the continuous variable, they are still like a little bit different for now. And in your case, for the continuous variable, is it limited by the detectors that you have in hand for the homodyne detection, or no? What is the limitation for the bit rate up until today for the continuous variable?
It's still the limitation comes from the level of security that you need. So what happens is that you can't work with too low SNR, because then you have penalties, and that limits some of your reach, because then you're going to lose that SNR. But you can't have it also very high, because then it stops being quantum, right? So what dictates the optimal is based on that, on the security level that you can work, and these are the two limitations. So everything that has been published up to now have limitations that are coming from 12 to 20 dB of budget, and using different assumptions for the security. So if you use simpler assumptions, you get 20 dB. If you use more strict assumptions, you get to 12 or so. Having said that, what we see, it's a large progress on how to do that. or increasing that, because there is more and more tricks that you can apply that come from the classical world that can help with the digital signal processing and help you, as well as more efficient algorithms for the error correction and the other aspects. So we believe that you're going to be able to get reliably and securely about in the order of 100 kilometers. And you may be able to get at the peak, right in the beginning, right, of the order of megabits per second. However, with the discrete variables, you can get, you can't ever get to the megabits. You're going to be limited to some kilobits. But you can go probably much larger distances, right? There has been demonstrations of 300, 400 in fiber, 400 kilometers in fiber. If you go to the free space, then it's thousands of kilometers, right? You have China demonstrating quantum key distribution with the most recent with South Africa, but before that with Austria. So they already been doing that.
Thank you very much, Valéria. While we set up our next talk, I have some announcements. First, we'll have lunch here, so you don't need to go out of the institute. At